The maximum a posteriori criterion is the optimal design criterion for a detector in a digital communication system. It is the criterion that minimizes the probability of error. In this video, we will particularize the application of the maximum a posteriori criterion for Gaussian conditional distributions of the observations. The maximum a posteriori criterion establishes that the observation Q0 must be assigned to the decision region of the symbol that maximizes the posterior probability. In an example, if here we have 4 symbols with the corresponding 4 posterior probabilities, we can find the maximum of these probabilities for the whole space of the observations. This is the maximum at every point of Q, and the decision region for a given symbol is just given for the values of Q, where the posterior probability is higher for this symbol than for any other else. For instance, these are the decision regions for this very simple example. Now we'll use the base rule to rewrite the posterior probability of the symbol BI as the ratio between the product of the prior probability of symbol BI times the conditional distribution of the observation given the symbol and divided by the marginal distribution of the observation. And if we take into account that there is a unique association between the symbol of index J and the vector of index J representing the signal that is transmitted for this symbol, so the conditional distribution of Q given B is equal to the conditional distribution of Q given A, given the transmitted symbol. Taking this into account, the map criterion can be written as follows. Here we have the posterior probability for symbol BI, here we have the posterior probability for symbol BJ, and the observation Q0 is associated to the decision region of the symbol BI when the posterior probability is higher than for any other symbol. In this comparison here, the distribution of Q is a non-negative quantity. We can remove this term in the comparison, and here we have the final expression for the maximum a posteriori criterion, where here the probability of BI can be replaced straightforwardly by the probability of the vector AI representing this symbol. In this comparison, we are comparing the probability of every symbol times the conditional distribution of the observation given the transmission of this symbol. Usually, the conditional distribution of the observation given a transmitted symbol is a Gaussian whose mean is the transmitted symbol and the variance is n0 halves in any direction of the signal space. Here we have a one-dimensional example. This is Q. The conditional distribution given A0 is a Gaussian with mean A0. The conditional distribution of the observation for symbol A1 is a Gaussian centered at A1. Now each Gaussian is multiplied by the probability of the symbol, the probability of A0 and the probability of AY, and the decision region for A0 is given by the points where this product between the probability of the symbol A0 and the conditional probability of the observation given A0 is higher than this product, the probability of symbol A1 times the conditional probability of the observation given the symbol A1. The decision regions in this case are defined by a threshold at this point when we have that the two terms are equal. This is the threshold QU that can be computed, and that depends on the different probabilities, the probability of A0 and the probability of A1, and depend also on the noise variance, depends on n0 half. With these decision regions, the probability of error has two terms. We have the probability of transmitting A0 times the probability of having an error in this situation, and we will have an error if the distribution when we transmit A0 lies in the decision region of A1. This is what we have here in blue. This corresponds to this area. The product between this and this corresponds to this area in blue. And then the second term is the probability of transmitting A1 times the probability of having an error in this situation. And this is the probability of the observation lying in the decision region for A0 when the transmitted symbol is A1. This second term, the product between the probability of transmitting A1 and the integral of the conditional distribution of Q given A1 out of the decision region of A1, this is in the decision region of A0, corresponds to the area in red in this picture here. And the probability of error is the addition of the area in blue and the area in red. To understand the probability of error as the addition of these two areas, the area in blue and the area in red, is convenient to remark that this is the detector with the lowest possible probability of error, because if we modify the threshold defining the decision regions with a higher value or a lower value than the point where we have that the product between the probability of a symbol and the conditional probability of the observation given this symbol are equal, the probability of error will be obtained by adding the corresponding areas in red and blue, and we'll have a higher addition here and a higher addition here, because with respect to the result that we have here, to this area in red and blue, we will have this additional area in this case, or this additional area in this case. So the maximum a posteriori criterion is providing us with the detector having the lowest possible probability of error.